$5,000. That is what her walls cost. She was living out of a Honda with her daughter in the back seat, and 11 months later she was standing inside a house with walls 18 inches thick that felt like cut stone under her palm. Those walls were dirt. The same dirt that was already on the lot. But here is the part that should bother you. The United States government published the instruction manual for this in 1926 and sold it to farmers for 5 cents, and today, following it is almost impossible to get approved. Her name is not in any newspaper archive, and it is not going to be, because women who quietly solve their own housing problem do not make the news. So call her what the permit file calls her, an owner builder. What survives her is the arithmetic, and the arithmetic is all public record. Start with the number, because the number is where everyone gets stuck. $5,000 for a permanent structural envelope sounds like a lie until you break it into parts. The soil is free. It is sitting under the topsoil on almost any rural lot in America, and the excavation for the foundation trench produces most of what you need before you have spent $1. The stabilizer, Portland cement at around 6% by weight, is the only real material purchase, and on a small footprint that runs a few $1,000s delivered on a flatbed. The formwork is plywood and dimensional lumber, bolted together, stripped off the finished section, and carried to the next one. You buy it once and use it 40 times. The compaction equipment is a pneumatic tamper you can rent from a yard by the week. The labor is where it gets interesting, because the Department of Agriculture actually measured it. Their estimate was that 3 men could place 54 square feet of 18-inch wall in a single working day. That figure came out of a federal labor study a century ago, and it has not changed, because the physics has not changed. She did not have 3 men. She had weekends, a neighbor who owed her a favor, and roughly 11 months of patience. Back up to how she ended up on that lot in the first place. Rent in her county had climbed past $1,300 a month for a 2-bedroom apartment. Her income could not touch it, and the waiting list for subsidized housing ran years deep. What she could afford, barely, was 5 acres of raw land an hour outside town, the kind of parcel that sells cheap precisely because there is nothing standing on it. But land without a house is a legal problem. You cannot live on it. You cannot get a construction loan against it without a builder, a stamped set of plans, and a bank willing to finance the design. She had none of those. What she had was a library card and a search that led her to a scanned government pamphlet from 1926, Farmer's Bulletin, number 1500, written by Betts and Miller, printed by the Federal Printing Office in August of 1926, and mailed out to farmers across the country during a decade when rural Americans needed to build cheaply and had no cash to do it with. This was not a pamphlet of encouragement. It was a technical manual. Soil selection criteria, form construction drawings, compaction sequences, wall finishing methods, labor estimates broken down by crew size. The government sold it for 5 cents, and inside it, a line written by federal engineers that reads today like something nobody in that building would sign off on now. No permanent building material is cheaper. The bulletin documented English construction where rammed earth walls, called pieds de terre, came in around 35% under the cost of hollow brick, and in one case, the gap ran far wider than that. Those were the numbers the United States government printed and mailed to its own citizens, and that scanned document is sitting in the archive right now, fully legible. She printed it. Then she went outside with a shovel and dug a hole. The first thing you do is test the dirt, and the test costs nothing but a jar. Fill a clear glass jar about 2/3 with soil taken from below the topsoil line, top it up with water, shake it hard, and leave it on a windowsill overnight. The particles settle in order. Sand drops first and forms the bottom band. Silt settles above it. Clay stays suspended longest, and lands last as a fine layer on top. What you want is roughly 70% sand and gravel against 30% silt and clay. Too much clay and the wall cracks as it dries. Too little and it never binds at all. Her soil was sandy loam sitting over a clay seam about 4 feet down, which is close to ideal, and she learned that from a mason jar on a kitchen windowsill. Then the wall goes up in lifts. You bolt the wooden forms into position on the concrete stem wall, plumb them, and brace them hard, because compaction pushes outward with real force, and a blown form will bury your afternoon. Then you shovel in damp soil to a depth of 6 or 8 inches. The moisture content matters more than anything else in the entire process. Squeeze a handful in your fist, and it should hold its shape and break clean, not smear, and not crumble. Then the tamper comes down on the first lift. It strikes the surface in a slow rhythm, working across the layer in overlapping passes. The loose material densifies under the blows, and the particles lock hard against each other. And here is the detail that separates people who have actually built these walls from people who have only read about them. The sound changes. Loose soil swallows the impact with a dull thud. As the layer compacts, the pitch climbs and sharpens until the tamper rings against the surface like it is hitting rock. That ring is the signal. That lift is done. Add the next one. Neolithic builders in the Yellow River Valley were using this same feedback loop roughly 7,000 years ago, and among the oldest compacted earth objects ever excavated at the Bonpo settlement is not a temple or a tomb. It is a cooking stove. Pressed earth, hardened without fire. Which tells you something about how far they trusted the material, because ordinary people do not run experiments on the thing their dinner sits on. When her wall reached full height, she unbolted the forms and pulled them away, and this is the moment that breaks people's expectations. There is no cure time. The wall stands immediately, striated with visible horizontal bands where each lift met the next, cool to the touch, hard enough that a hammer bounces off it. 18 inches of compacted earth weighs roughly 140 pounds per square foot. It is monolithic, which means the structure and the material are the same object. There are no mortar joints to crack and no assembled seams to separate. Assembled walls fail at their connections, and this wall does not have any. The Hakka people in China's Fujian province built entire fortified villages out of this material between the 15th and 20th centuries. The Fujian Tulu are circular and rectangular earthen buildings 4 stories tall, some of them housing hundreds of people inside a single ring, with walls thick enough to resist cannon fire. 46 of them are still standing and inhabited, and UNESCO listed them as a World Heritage Site. Farmers built them without a single engineer's stamp. Now the part that made her utility bill collapse. In 2008, researchers Matthew Hall and David Allenson published work in the journal Energy and Buildings, measuring how stabilized rammed earth actually behaves as a building material, and what they found does not fit inside the metric American energy codes are built around. Modern codes judge a wall by R value, resistance to heat flow, and by that single measure rammed earth looks mediocre. Its thermal conductivity sits somewhere between roughly 0.6 and 1 watt per meter Kelvin. A cheap fiberglass bat scores better on paper. But the wall is not trying to block heat, it is storing it. That enormous mass absorbs energy slowly and gives it back slowly, so the afternoon sun that hits the south face enters the wall and comes back out around midnight, when the desert air has dropped 30 degrees. The morning chill soaks in and returns at dusk. The outdoor temperature swings violently, and the indoor temperature barely moves. Her house lags behind the weather instead of fighting it. Hall and Allenson measured a second effect that the codes have no column for. Rammed earth is porous and hygroscopic, which means it trades moisture with the air around it. When indoor humidity climbs from a shower or a pot of soup on the stove, the walls take it up. When the air dries out, the walls hand it back. Across both summer and winter conditions, the material damped indoor humidity swings significantly, keeping interior surfaces out of the range where mold takes hold, with no mechanical ventilation running at all. The walls were doing the job that a bathroom fan and a dehumidifier normally do on your electric meter. They also found something that annoyed their own predictions. They expected denser walls to conduct heat faster in a clean, linear relationship. It did not appear. Conductivity showed no direct correlation with maximum dry density, because the microstructure and the particle contact patterns mattered more than the raw weight. The dirt outperformed the model. There is one caveat, and it is not optional. Wet walls conduct heat far faster because water fills the pores and builds thermal bridges straight through the mass. Every surviving rammed earth tradition on Earth solves this the same way, with deep roof overhangs, a raised concrete stem wall, and drainage that pulls water away from the base. She built a 30-inch overhang on every elevation of the house. The technique works if you respect water, and it fails fast if you do not. Meanwhile, the ground below her frost line sits near 54 degrees year-round, and it manages that without a furnace, a thermostat, or a monthly invoice. If this is the kind of thing you want more of, subscribe. Next week, I am opening the file on the solar wall that heated houses with a sheet of glass and no moving parts, and how it disappeared. David Easton has been building rammed earth structures in the United States since 1976, and his company, Rammed Earthworks, has completed hundreds of residential and commercial projects across the American Southwest in the decades since. His 1982 book, The Rammed Earth Experience, put the method into the hands of owner-builders who had never heard the word pisse, and he has been revising and reissuing that material ever since. Architect Rick Joy finished the Catalina House in Tucson at the end of the 90s, its rough striated earth shell photographed in architecture magazines worldwide. In 2016, the Aleutian Housing Authority built a stabilized rammed earth home in Alaska, with federal housing support, using an insulated sandwich assembly to meet cold climate requirements. The federal government helped put an earth house up near the 60th parallel. Western Australia's State Housing Department, working with the University of Western Australia, committed to roughly 300 rammed earth homes across remote Aboriginal communities in the Kimberley region. That was not a pilot program. That was housing infrastructure at scale, in one of the harshest building climates on the planet. And New Zealand wrote the clearest rules of anyone. In 1998, they published a national standard covering adobe, pressed earth brick, and rammed earth for builders not requiring specific engineering design, with a direct compliance pathway for structure, durability, and external moisture. Same physics, same material, different policy. In New Zealand, you do not need an engineer to build a house out of earth. In most of America, you need an engineer, an attorney, and a very patient bank. Which brings us to the wall she actually struggled with, and it was not made of dirt. Open the International Residential Code, the document that governs how homes get built across most of the United States, and turn to wall construction. You will find exhaustive prescriptive tables for wood framing, stud spacing, sheathing thickness, nail patterns, header spans, every dimension resolved in advance so a builder can follow the table and pass inspection with a tape measure. Search that code for rammed earth. There is nothing. That is not an oversight. The International Code Council states plainly that the conventional construction provisions are prescriptive and intended for repetitive light wood framing. The tables assume lumber. The insulation pathways assume hollow cavities. The entire compliance structure assumes you are building the same house that has already been approved 10,000 times. If you are not, you fall into the alternative materials section, which allows a building official to approve something unconventional when equivalence is demonstrated. That pathway is real, and it is how her house eventually got a permit. But the burden of proof sits entirely on you. You provide the engineering documentation. You pay the licensed professional. You fund the laboratory testing. She was pricing soil cylinder tests and stamped drawings against a wall that was going to cost her $5,000 in materials. And on a house that small, the paperwork can genuinely cost more than the thing it describes. And structural approval was only the first counter she had to stand at. The Energy Code expresses its requirements as R values by climate zone, written around cavity insulation and continuous insulation, built on the assumption that a wall is hollow and stuffed with something manufactured in a factory. A solid monolithic earth wall does not fit any row in that table. Its thermal mass, the entire reason it works, is invisible to the metric that decides whether it is legal. Builders often end up bolting rigid foam onto the outside to comply, creating hybrid sandwich assemblies that add cost and complexity to a system whose whole advantage was simplicity. Then comes the money, and this is the part she could not fight at all. In 1936, the Federal Housing Administration published its Underwriting Manual, the document that shaped American mortgage lending for generations. It built the sales comparison approach that appraisers still use, and it trained an entire profession to reward conformity and mark down anything that departed from what the neighborhood already had. Unusual materials did not add value in that system. They subtracted it. That logic never fully left the building. Fannie Mae's current selling guide acknowledges the problem without solving it, instructing appraisers that when no truly comparable sales exist because of a property's uniqueness, they must use the best available indicators of value and make market-supported adjustments. In practice, her earth house gets compared to stick frame houses down the county road. The uniqueness she paid extra to permit becomes the discount she absorbs at appraisal. Insurance closes the circle. Most American states have no standardized actuarial category for rammed earth construction, no premium tables, and no loss history for an underwriter to price against. Some carriers write these policies case by case, many just decline the call. And in most jurisdictions, there is no contractor credential for earthen building either, no certification, no continuing education pathway, and no inspection checklist for the thing you are putting up. Nobody banned this, they just made it expensive to be legal, which is exactly why she built where she built. New Mexico has explicit earthen building code provisions, and they are specific. Exterior rammed earth walls a minimum of 18 inches thick. A 2-story height limit. A compressive strength requirement of 300 pounds per square inch, verified by a certified laboratory testing cylinders of her actual soil, with the results submitted alongside the permit application. The code even names which stabilizers are off the table. That is what a functioning pathway looks like. Prescriptive, documented, and buildable by one person, with a permit application and a soil sample. It exists in one state. In the other 49, you start from zero. Follow the money, and the shape of it stops being mysterious. The United States cement industry shipped roughly 110 million tons in 2024, worth around $17 billion. Weyerhaeuser, a single timber company, reported net sales near $7.1 billion in the same year. When your wall is the soil already sitting on your own lot, you buy almost nothing that those industries sell. You cannot meter dirt. You cannot patent compaction. There is no service contract on a wall that holds temperature by being heavy. Even the American Standard Guide for Earthen Wall Building Systems concedes that earthen construction has fallen into disfavor in places where it was once common. Displaced, not disproven. Her rent line is zero. That is the whole ending. No landlord, no monthly transfer, No increase letter taped to the door in January. Her daughter has a bedroom with a wall so dense that the room stays quiet when trucks pass on the county road. The house cost her a used car's worth of cement, a rented tamper, 11 months of weekends, and a fight with a permit office she is still not entirely sure she won. Press your hand flat against a wall like that and it feels like stone. Cool, solid, dead silent. It is dirt. It was always dirt. It has been holding temperature and standing against weather for 7,000 years. And it is sitting under every construction site in this country right now, waiting, while somebody 1,000 miles away ships in the materials we decided to call normal. Send this to whoever is renting and doing the math. Next time on the archive, the wall that heats itself. A sheet of glass, a mass of concrete, no furnace and no moving parts. The Trombe wall was patented, tested, proven, and quietly written out of the code in under a decade. That story opens in the high desert.